I welcome you all to the Spark Research YouTube channel. This is Dr. V. Chandra, Assistant Professor in the Department of ECE. So we are running currently in this series the COMSOL Research Applications. So we are going to talk some more design structures, the simulation, how to perform the simulation related to this photonic waveguide in this session. So primarily we are going to focus the simulations which can be done using this COMSOL platform. As an example, we are going to consider the photonic waveguide. So here is the detail about the institute, that is SAT-MIST, which is ranked on 14th, just above to the IIT ISM Dhanbad as per NIRF 2025 ranking. Okay, so what is this photonic waveguide? So if you are a new researcher, so here is the just as the glimpse about the photonic waveguide. So primarily your photonic waveguide actually is being used to transmit the information. But who is the carrier? Instead of the electron, your carrier is light. Question is, why are we talking about the light propagation? Simply because of faster speed, right? The speed of light is much more high compared to the speed of the electron. So this is the exactly the that is why we are talking about the silicon photonics. So if you wanted to know the more details about these things, silicon photonics, then please go to this Google Scholars. I have already discussed in my previous session as well. So either you can follow that video, or you can just go to this Google Scholar and find out some more interested article, right? Okay, so here now if you will visit the Google Scholar and if you will search this title, that is reanalysis of single mode conditions for silicon ray waveguide at 1550 nanometer wavelength, then you will get an article which has already been published in Journal of Lightwave Technology in the year of 2016, right? Means almost 10 years back. So you can find out the articles and you can find the different the objectives that you wanted to find out. So in from this paper here, just we wanted to implement this paper, nothing else. So I have taken this structure from this paper only, and so in this structure you can see this is your substrate layer, that is NSiO2. Then over it there is a silicon layer, so having the width, height, everything is given. So what are the height variations? 0.4 to 2 micrometer. Then the operating wavelength is 1550 nanometer, and waveguide width variations we can vary it from 0.5 to 4 micrometer. So we'll study the model analysis to find out these things like confinement factor, effective refractive index, then the propagation loss, all these things, right? So we are going to design this structure only. All right, now we are going to start to design our simulation structure using the COMSOL Multiphysics. So here is an icon, just double click on this icon. We'll start to design our simulation structure on the console. So as have the two different wizard, blank model and model wizard. So blank model is primarily being used only by those persons who are very experienced to design structures on the console, because they have to choose everything by themselves. But model wizard is easy comparatively, because here by default the parameters are given by the console only. Okay, so we are going to choose model wizard. Under the model wizard, now we have the different options. What are these are the space dimensions. So like whatever the types of the structures you might have, based on that you can choose your structure space dimensions. So of course 3D is little bit complex. Why? Because if you are going to design your structure in 3D, then it will take much more time to simulate. Also 2D is asymmetric than 2D, 1D asymmetric, 1D and 0D. So for the time being we are going to design our structure using the 2D, right? So just click on the 2D. Now here you can see there are the different modules. So AC/DC module can be used by the persons who wanted to study these related fields like electric fields, magnetic fields, all these. Similarly, acoustic, the modules, these can be, the used to study the pressure, chemical people's chemical species, then the fluid flow, heat transfer, structure mechanical. These things are being used by the mechanical peoples, like how to study the heat transfer and all those things, right? For the time being, we are going to talk about the optics module. This one, why? Because we are going to talk about the light propagation only. So here there are the two options, ray optics and the wave optics. So ray optics is primarily being used by the persons, those who are studying the particle nature of the light. Since here we are going to talk about the wave nature of light, so we will choose this wave optics module. Now under the wave optics module, there are the different methods to study the wave propagation, right? So electromagnetic wave, beam envelope method, then boundary element method, then frequency domain method, time explicit transient. These are the method. So we will choose the frequency domain method, right? Then add, click on the add, then click on the study, right? So now for study, now after choose that deciding your models, now you have to choose what type of study you wanted to perform, right? So either you wanted to do the eigen mode, frequency model domain, then adaptive boundary model analysis. So of like frequency domain model, then the frequency. So what type of the study you want to do? So for the time being, we are going to study the mode analysis, that is how the light will propagate, that is what type of mode will form. So mode analysis only, then click on the done. So now after clicking on done, now you will get this type of interface. Now we are actually going to start to design our structure using the COMSOL. So first of all, we are going to assign the parameters, that is input parameters. What are the inputs parameters? Like we are going to set that will be used in our design structures. Then we'll assign the definition sections you may assign if you need. Then geometry, you will have to design the geometry. Then we'll assign the materials. Then we'll provide the input wave, then we'll design the mesh, and finally we'll what are the study you wanted to perform, we have to enter the details. Then finally after computing you will get the results here. So these are the major steps, right? So what are the steps? We'll follow the parameters, then geometry, material, input wave, mesh, mode, study, these things, right? So let's go one by one. First, for our structures, what are the major parameters we are going to consider? Since we are going to design the strip or the reach type of the waveguide, so let's enter the details. So W, let's suppose WSIO2 width is your 4 micrometer. Okay. So once you will enter, then automatically these details will become here. So now again we are going to define the height h SiO2. Why I am considering SiO2? Because the SiO2 is the silica glass which we are going to use it here. So as per the material I am assigning their name, like then W, that is width of silicon. So these are the values, whatever the values we are considering, these are the very standard parameter, right? So in your research articles, you can find these details. So HSI is your how much? 220 nanometer. Why I am using 220 nanometer? Because the single mode will propagate in this dimension. So in order to propagate the single mode, we have to choose these dimensions. And for base dimensions, like whatever we have chosen it here, that is that's assumptions, you can choose longer than that, no problem. So these are the parameters we are going to use it here in our structures. So it's not mandatory, but exactly this will be useful for our design structures. So we'll see that is what is the importance to use these input parameters to design our simulation structure. Lambda is your wavelength. Why are we talking about this 1550 nanometer only? So search and find out the details. Actually this is a third optical window only, okay? So the transparency window, so find out what is the reason behind it. Geometry, now let's go to the geometry. So as per our geometry, our first base we are going to use, that is of rectangular shape, so rectangular only. Then type will be solid only, no curve. Then width, like since we are going to design our structure in nanometer scale, so here length unit we can change it from meter to nanometer or micrometer, okay? So nanometer I'm choosing. Now with suppose if I wanted to I don't want to use the parameters, then in that case you can uh, the define like that, and you can get the after build your selected build objects, you can get the structure like that. But since we have already defined our parameters, so here we are going to use the nomenclatures that we have already assigned in the parameter section. So WSIO2, then height is HSIO2, right? So here is our structure, the first structure. Then base is center. Why is this center only? Because now see here, uh, this is your center 0 0. So here minus 2000 and right side plus 2000, so total is 4000. Similarly minus 500 below and plus 500, that is on the y-axis, total 1000 nanometer. So that is why this is centered at the the center, your geometry centered. So that is why we are keeping 0 0. Similarly, now we will design another structure. So now we are going to keep one more rectangular shape structure on above to this SiO2 platform. So to do so, now we'll choose the another rectangular shape. Again, solid width will be the now WSI. Then what will be the height? Height will be HSI, right? Again, we are going to choose the center x-axis, exactly we are going to keep it here. So from x-axis point of view, it will be centered again at 0 only, but y-axis now it will be shift. How much it should be? So first of all, this much from 0 to this means h of this half portion means to 500. Then again we are going to keep it here, now center will be at this point, so y-axis will be shifted your HSI by 2, right? So y-axis will be shifted like HSIO2 divided by 2 and plus HSI by 2, right? So in this manner we are going to shift SiO2. Okay, here is your plus. Okay, so now we have assigned the another structure, Si structure, right? Now in order to simulate, we are going to draw another one more structure, so that now here W will be WSIO2, then here HSIO2, and yeah, x-axis exactly it will be centered, but y-axis will be H of SiO2, right? So this will be half and we are going to keep it here, so half. So now total, so we have this structure now, okay? So geometry is over. Now we are going to define the material, right? So here you can do two things. First, either choose the material from library or blank material. You can, if you wanted to choose a blank material, you can design, no problem. For the time being, we are going to choose the aid from library. Okay, so here is your library. So we'll choose it from the built-in reason. So what are the materials we are going to use? This will be your SiO2, this will be your silicon, this will be your air material. So we'll choose air, and then just double click whatever the materials you wanted to choose, right? Then silica glass we are going to use, then silicon we are going to use. These are the materials we are going to use. Suppose if you don't if you are unable to find out your materials here, then you can define using the blank material and assign their properties, right? Now in which reason you have to assign your material? So air, like first check, there are three different domains. So domain 1, is it belongs to air? No. Then remove domain 2. Yeah, this domain belongs to the air material. Domain 3, is this domain belongs to the the air material? No. So remove this. Now silicon, silica glass. So which region is of silica glass? This one. So just blue color selected. So now this is your domain 1. Silicon, which region? Now this region, right? So now check, air belongs to domain 2, silica glass belongs to domain 1, silicon belongs to domain 3. So we have already assigned the material in this manner. So geometry material over. Now, what is next target is to give the input. So here electromagnetic wave frequency domain. So wave already it has default values. It has given like input wave in all these domain, and also the perfect conductor initial values. So no one need to do anything in this thing in the electromagnetic wave. So this is default electromagnetic input wave, right? Now mesh. Now how will design the mesh? Mesh will actually perform the study. How will it perform the study? So either it will be physics control or maybe the user control. So user control means you have to define everything by your shape, size, everything, right? And under the physics control, they will define the physics control. Okay, so again normal, and these are the different the options that you will get. So I'm choosing normal only, and then click build all. Then these are the mesh is what? Mesh is the actually division of your structures, and since the more number of mesh means more division of your structures, means it will study your the simulations more accurate. So more number of the triangular shape, that is more number of mesh means more accurate. But problem is that if you have the much more high number of mesh, it means it will take very much long time to simulate your structure. So in order to avoid the simulation much more time, you can use the normal, so that you can have the average number of the mesh. Okay, also you can choose the extremely file, you can check it here. So more number of meshes are there. For the time being we are going to consider normal only. Okay, so you can also use the user control. In this case you have to define everything by yourself, right? You have to choose the maximum element size, minimum element size, growth, curvature factor, resolution, everything you can choose, right? So for the time being we are going to consider the physics control normal only. Now lastly, what are the study you wanted to perform, right? So you have to assign exactly that one only. So here suppose I wanted to perform the study modal analysis frequency. So here we have to provide the lambda. We have already assigned lambda as an wavelength having the frequency of 1550 nanometer. That is our wavelength. Okay, so desired modes you can choose how many modes you wanted to study. For the time being let's consider 4. And the modes, where exactly we'll study the modes. So maximum refractive index that we have considered in our design structures. So for the time being silicon have the highest refractive index, that is 3.48. You can check it here. silicon refractive index 3.48. This is the refractive index. Now, why are we assigning these refractive index? Because these are the belongs to the optical parameters. So since we are studying the photonic, so optical parameters is only useful. Okay, then nothing to do. Now simply compute. Click on the compute and just wait for a few seconds. Since I have considered very normal structure, so it will the simulation time is very less and we got the results, right? Now see, the light is actually, what is this? So this will give you the intensity of light. So blue color means the very less intensity, red color means very high intensity, right? So here you can observe light have the highest intensity in the substrate region. This is your silica and this is your air and this small portion is your silicon. So is this propagating mode? Of course no. So since we have studied the four modes, so let's check another mode. This is your another mode. Light is still not propagating properly in the silicon region. Okay. This is another mode. Still light is not propagating. Here this is another mode. This is the very perfect, right? Here you can observe light is mostly propagating through the silicon core, silicon mode. That is the this is the mode propagating mode, right? Others are the leaky mode because light are not able to propagate through the silicon region. This is high index material or the core. So this way we can study the whether light is propagating or not, and then we can find out the different parameters. So here if you wanted to find out the parameters, then you can go and you can check the derived values. Okay, how to go derive? Just click the right click, global evaluation and expression. You can put the expression here. Like suppose I wanted to calculate an effective. Okay, so effective mode index for the different mode, then click on the evaluate. So you will get this. Similarly, suppose I want to calculate the real part or the any parameters, whatever we wanted to calculate, you can use the equation and find out. So like this manner we can find out. So since the session is going longer, so I am stopping here, but in another session we will discuss about how to find out the different parameters, including the confinement factor, propagation loss, even a scan field, and the coupling length. Much more things we can find out. Different propagation, different the and parameters. Also we'll see the some more depth of the mesh, how to design, then the study how to perform more study. So these are the things that we can continue to study. If you have any problems, drop your comments. Thank you to join the session.